Go.
Good morning, ladies and gentlemen. Okay, so we have these sliders here, this ruler and this centerpiece here. And what I'm gonna do is I'm gonna leave the sliders alone, and I'm gonna balance the system by moving the pivot point.
What are the masses you've got there?
This is 0.5 kilograms and is that 200 grams?
0.2.
0.2.
200 grams,
0.2
500
kilograms.
grams.
Okay.
So
how do I...
the big heavy one, the massive one is the one over here on the left. What should she do with the ruler? Which way should she move the center?
Let's see. What if I go... This is pretty hard to move. That's not working, right? Let me try that.
That's the wrong way.
More. More. Oh, too much. Will Miss Moore get it? Harder than it looks, people. Oh. Ooh, we're almost there.
Okay, that's pretty good. So notice that you had to move the center point, the balance point, closer to the heavier one and farther away from in order for it to even kind of balance.
And that's important, right? The center of mass is closer to the one that has more mass.
More mass, yeah.
Okay, so...
It's like a weighted average.
It is. So this balance point is called the center of mass. You guys have heard those words before.
You might have heard center of gravity, but center of mass is a much more better one. Oh!
Okay, so I bet you guys I can find the center of mass of this ruler without even looking. Right? Oh. Okay, it looked a little bit. Okay, so what's happening there? What's going on? Okay, what am I doing? What is the center of mass? This is the balance point.
Well, you got to this because that meter stick is uniform in mass. The center of the meter stick would be the center of mass.
And you know, I forgot to mention one thing about the our what do we call it over there?
Balance beam. Let's call it the balance beam.
So one thing I forgot to mention is, you know, this is not a perfect system here. Ideally, this would only be 100% accurate if the meter stick had no mass. If we had a massless meter stick.
Yeah, that's right.
But we have, you know, more of the meter sticks over here, more mass, so it does throw it off a little bit. But when we do these sorts of problems, or when we look at this, we just have to pretend like the meter stick does not have
no mass. It's like no air resistance, no absence of friction.
Yeah.
It makes things easier.
Okay. How could we predict where the balance point would be if we hang a 200 gram mass at 5 centimeters and a 500 gram mass at 95 centimeters?
Think about that one, y'all.
How can we do this? In a one-dimensional horizontal system of two bodies,
like those two masses over there,
the position of the center of mass is this. Mass 1 times position 1 plus mass 2 times position 2, all divided by mass of the total mass.
The total mass.
Mm-hmm. So like we talked about, it's notice that it's like a weighted average.
So let's go back and use those numbers where we had a 200.
Oh yeah, what was it? Here we go. We had 200 grams. Mass 1 is 200 grams.
Yep.
And position 1 was
5 centimeters.
Now, should I make it, should I go to meters or can I keep
No,
that
just keep centimeters. It doesn't matter.
Okay, someone had a question about that today, and I was like, I guess it depends.
Some things, it depends. If you're using forces, you got to have newtons and meters and seconds.
And then it was at 95.
95
centimeters. Okay. All right,
what was that equation again?
Let's go to the equation. Okay, so...
I'm going to predict that the center of mass should be closer to the 500 than the 200.
Right, it's the heavier
just like
one.
we saw when we were playing with the thing over there.
Okay, so mass 1 is 200 grams. Position 1 is 5 centimeters plus 500 grams times 95 centimeters, all divided by mass 1 plus mass 2, which is 700 grams.
You did that in your head.
What do you say, the human calculator? Okay, so now I will use a calculator.
200 times 5 is 1,000.
Oh, maybe I don't need
Five? No. 500 times 95. I'm choking on that one. It's going to be 400 and
500 times 95 is
475. I'll bet.
Okay, yes.
Woohoo!
1,000.
The human calculator.
So I get, and this isn't everything. This is 48500 divided by 700 centimeters, grams. So divided by 700. I did not need to read that out. I'm gonna call it 69.3.
69.3. That's closer
Grams
to the
service.
500 gram than it is to the 200 gram.
Yeah.
Boom.
Okay. Well done. Well executed. Okay. So notice that this is almost like a weighted average. Oh, we already did that. Okay, moving forward. What would happen if the center of mass to the center of mass if one or both were moving?
Huh.
Let's go ahead. Let's take a look over here at. Bring this over here. All right. So this is good old PhET, our PhET simulation, and what we have here is the first ball and the second ball, and they have a mass of 0.5 kilograms and 1.5 kilograms. Now check out what happens, and this X right here represents the center of mass.
Oh.
And this one has more mass, and notice how the center of mass is closer to that side, right?
Yep.
Now what happens if I make this one have more mass?
So as you increase the mass, the X moves closer to the heavier thing.
Yeah, well, check that out, right? Okay, so I'm gonna go ahead and push reset. I'm gonna make this just like how we had it before. 0.5 and 1.5. All right, sweet. Okay, so what I'm gonna do is I'm just gonna go ahead and push go, and I want you to watch the X.
Whoa.
Whoa. I'm actually gonna go normal. Push your foot there, okay? And again, watch the X.
Okay, the red one bounced back in the other direction. The other one sped up, went off, but the X kept going at a similar rate.
It's going in the same direction, going at a similar rate. It's not speeding up, it's not slowing down. It's unchanged.
So the center of mass was moving in the simulation.
So yeah, so what would happen to the center of the mass? Well, it's unchanged. It keeps moving in the same direction.
We'll get to that in a minute.
It doesn't speed up. Okay. Oh. Displacement of center of mass. So before we had the position.
You don't have to write this down.
This is just the displacement, and we just put in our delta here, our change in position.
Yeah.
This really just tells us, it just gives us a direction, right? That's the only difference between distance and displacement. Okay, now this one you need. Velocity of center of mass.
Okay, so you start off with X, and then you put in delta V, and now you put in V. What do you notice about this?
Well, what is mass times velocity?
What have we been studying here?
Momentum, right?
Boom!
So this right here is basically the momentum for this first ball, and this one would be the momentum for the second ball. And together they'd be the total momentum.
The total momentum.
Right. And then these are just the masses of the balls.
Divided by the total mass. Interesting.
Okay. Now, the numerator is the total momentum of the system. We just talked about that. What does the law of conservation of momentum say about the velocity of the center of mass?
I don't know. Momentum before is equal to momentum afterwards.
So that means the velocity should be the same before and after, right?
I think. Yes.
Okay. So here we are, momentum before, momentum after totals are equal to each other, and we can say, we can have momentum total, and over here we have the velocity of the center of mass, and then our two masses.
Go back to that equation. I agree with that. Go back to that equation, this one right here. You've got the total momentum on the top.
Total momentum here.
And divided by the total mass, and then go back to that slide we were just looking at. I don't know if I got my short-term memory loss.
Oh, wrong way.
No, there you
go. Okay, so we talked about total momentum.
And that total momentum is the sum of the two that we had on the top. And if that was divided by the velocity of the center mass, so that's saying that the center of mass is not going to change. Because the momentum doesn't change, the mass isn't changing, and so the momentum doesn't change.
The momentum doesn't change because the center of masses don't change.
Yep.
So what we're saying is, I'm going to go ahead and write out my velocity for the center of mass equation. It's basically P1 plus P2.
That's an M1 V1 plus M2 V2, right?
Yeah, exactly. Okay, divided over mass 1 plus mass 2, right?
Yep.
And from here, we know that this equals,
well, the momentum of one plus the momentum of the other, that's the total momentum.
I was like, what was our next step again? So this plus this is going to give me the momentum total.
Over M1 plus M2.
Yeah, over M1 plus M2. Okay, so how can we get this to look like this?
Whoa!
Oh,
too close.
Well, we already have this over here. That's this, right?
That's, yeah.
Okay, now
We've got to divide by the M, okay, you've got to multiply.
Let's go ahead and just multiply this, right? If you multiply this by M1 plus M2 over here, they cancel. M1 plus M2 is over here now. Well, this equals our total momentum. And we know that the total momentum in a system is conserved.
It's not changing.
Right? It's not changing. And so if we have masses that are unchanging,
that's not changing,
then this also is not changing as well.
Okay.
And that's what we're talking about.
It's a logical progression. Well done, Miss Moore.
Right here. Okay. The velocity of the center of mass of a system cannot be changed, we just said this, by an interaction within the system, a collision or an explosion. Velocity is unchanged. So
we can use this to solve for situations where we have two unknowns.
So go ahead and write these down in your notebook.
It won't make any sense right now, but we're going to show you how to make it work.
So find the velocity of the center of mass. We just had an equation for that, right?
Yeah.
Subtract the velocity of center mass from each one. Change the signs of each one. And the velocity of the center mass, add the velocity of center mass back to each. Works for unknown V prime.
Yep, it'll let you know the V final. Okay, now rather than show you how to do this, we're going to give you a worksheet.
Follow the directions. You've got two balls that are rolling toward each other. Ball A has a mass of this and a velocity of that. Ball B has a mass of this and a velocity of that. Make a sketch of what's happening, and then follow the directions.
Read carefully.
What is the total momentum?
And if you get stuck, call up one of your classmates and say, what are we doing here?
Help me. Help me. All right, go ahead and begin, you guys.